Okay, so we've finished looking at electric fields, and today we're going to start looking at magnetic fields. Now, these are really closely related. That's hence the reason they follow on from each other, and we're going to see why that is very shortly. So, like I said, electricity and magnetism are really closely related. So, what we can do is, and this is how all electricity is created, we can move magnets to create electricity. All right, so if we get a generator moving, and we've got a magnet involved in there, and it's a bit more complicated than that, but basically we can use that to create electricity. Now, on the flip side, if we can use magnets to create electricity, we can use electricity to produce strong magnets. All right, these are called electromagnets, and you can see down here, often used in dumps or car crushing yards to pick up metallic objects and move them around. Now, those magnets are created using electricity, and they're called electromagnets. But we'll see that a little bit later. Okay, so the reason why this stuff is all very important is because we generate all electricity in using this process. We can create magnets that can be switched on and off, like we just saw with the large car moving magnet, the electromagnet. We can convert electricity into sound. Okay, so in all of your headphones, in your car, at home, all of your speakers use electricity, magnetism to create sound. And it's also used to generate radio signals, so Wi-Fi, Bluetooth, TV. So these are all really, really important concepts. So we've already seen that charges produce an electric field. Now what we're going to see, and what Hans Christian Ørsted, a Danish scientist, noticed, is that wires carrying a current, they generate magnetic fields. All right, and magnetic fields are created from moving charge, and we're going to see that. So stationary charge produced an electric field. We've already seen that. If we have moving charge, it produces a magnetic field. All right, so like I said, if we have a moving charge, we create a magnetic field. Now this is in addition to an electric field. So we still create an electric field, like we've been looking at in our previous topic. An electric field is still created, but we also get a magnetic field. Now, if we have a stationary charge, so just a charge that has no motion, it's just completely still, the velocity equals 0, then there's no magnetic field. There's only an electric field. So let's compare the two. So electric fields, firstly. These are created by charges. We know that. Okay, here's an example below. Now, magnetic fields, these are also related to charges, and they're either created by magnets, okay, or by moving charges. Now, we'll find out later that the magnets are a natural moving charge, but we don't have to worry about that yet. So that's how they're created, one by charges, one by magnets or moving charges. Our electric fields, they're either attractive or repulsive. That's the same for our magnetic fields. They depend upon charge for the electric field, and the magnetic field depends upon a pole. All right, again, we'll look at that. So last of all, the two charges, as we see below, they're distinct. We can tell them apart. Now, for a magnetic field, a little difference again is that the two poles, they're always connected. So you can see here we've got a magnet, one end's north, one end's south. We'll have a look again. These are connected, and they are always connected. So there's no magnetic field that just radiates outwards like this. They're always connected to a north and a south pole. Okay, but again, we'll see that in a minute. Okay, so how do we represent magnetic fields? You can see here we've got a bar magnet. One end will be north, one end will be south. And you can see it's surrounded by compasses. Now, these compasses are lined up in a very particular way. So if I follow the arrows, I get the shape like we saw with electric fields. Okay, so this is how we're going to represent magnetic field lines. And we're going to see a specific example on the next page, but again, if I follow the arrows, eventually they link up, okay, and we get the magnetic field. Now the direction is a little bit different based on something else, but let's have a look at that now. Okay, so we've got a bar magnet here, and I've labeled each end 1N, 1S, north and south. And what we see is that from our bar magnet, we have these magnetic field lines that flow from one end to the other, okay? And this is consistent all the way around. And as we move further out, we see a pattern that's very similar to our electric field lines, okay? We get two at the ends that just go straight along. Basically, we see this pattern emerging like this. Okay, so we get these magnetic field lines. The more we have, the stronger the field. And we know that, well, I've already mentioned that these are always closed. These are always looped together. You end up at the same spot. Now, the way we draw them, the direction is based on a couple of reasons. One, we'll learn later, the right-hand rule. But if we have a magnet like this, and we know the north and we know the south, it's always from north towards the south. So, from north towards the south. So, towards south from the north. Okay? You can see I've been consistent all the way through there. And that's how we represent them. Now, the more lines we have, it means the stronger the field, just like with electric. At the moment, this is all I need to show you, though. Okay, so again, just to reiterate, the field is represented by field lines, just like we were looking at with electric fields. However, they go from north to south. And the strength of the field, again, just like electric fields, is represented by the density or the number of lines. The more lines we have, the stronger the field. Once again, just like electric fields, it's a vector quantity. It has a size and a direction. And this is unlike electric fields, but our field lines always form closed loops. Okay, so they always come back. There's no never-ending like electric fields. There's no never-ending lines that radiate outwards. Okay, so what about an electric current? I said that if we have a north and a south, the magnetic field flows from north to south. But I also said that moving charge, like in a wire, produces a magnetic field, and that doesn't have a north and a south. So when it's not labeled, how do we know which direction the field is? Now, if we have a think about our other fields with our gravitational field, if we want to know which direction it is, we can let go of an object with mass and it will fall in the direction of the gravitational field. Okay, generally down towards the Earth in our context. Electric field, we had a small positive charge, and whichever way that moved, that's the direction of our electric field. Now, for a magnetic field, what we want to do is we want to use a compass. Okay, so that's the equivalent of our small positive charge. We want to use a compass, whichever the way that points, that's the direction of our field. And you can see here, we've got a wire, and the wire has currently got some current flowing through it. If we surround that by some compasses, they'll align in the direction of the field. And you can see they're becoming a circle here. And we're just going to have a look at that now as well. So if we want to find out the magnetic field, what it looks like around a point, for a wire, we use the right-hand curl rule. Okay, so that's a really important rule, the right-hand curl rule. Basically, what you want to do is get your right hand, your thumb goes in the direction of conventional current. Now, conventional current, we know current is the flow of electrons, but conventional current is the direction of protons. The reason for that is because they found out how to use electricity before they knew what it was. So, direction of conventional current or protons. And then if you let your fingers curl around naturally using your right hand, that's the way the electric field should go. So you can see here with the electric field lines we've drawn on this end, the magnetic field lines, they curl around in the direction of the fingers, and that's how we work out what it is. So all you have to do is make sure you use your right hand and your thumb points in the direction of the current. Okay, so just a little bit of notation here. Sometimes on our previous slide we saw that our wire there was clearly a direction to our wire, but sometimes the wires are coming directly at us and they're hard to represent, or a little bit different to represent. So basically the way we are going to do it is if the wire is coming directly towards us, it's going to look like either this or this. We just see a circle. Now, if the current is flowing towards us, we'll see a dot in the middle of that. If it's flowing away from us, we see a cross. The way we remember this is it's like if an arrow, like a bow and arrow, was coming towards us, all we would see is a little dot, the tip. And if it was flying away, we'd see the